I haven't studied much about eigenvectors and eigen stuff, and so I'm gonna put it on you. I'm gonna put my stress onto the viewer, and maybe some of those who will watch will share the stress with me. In which case, I'll double your stress. So let's get into the news. Um, I'm gonna teach this in such a manner that you probably won't understand because I'm gonna give you theorems and things I need to memorize because I already know how a matrix works. But I might do some proofs because you want to know how those go, right? So that's what we're going to do. The stuff is talking about maybe eigenvalues. See, there's two V's actually. Come to find values, vectors. There's the other V, spaces, and like other things probably. It's stuff. It's not just these three things. Then I might call it eigenvivs. Like, you get it. That's besides the point. But yeah, like on a conceptual level, I don't know what any of this is. But we're gonna start out simple. We need the basics. We need to start with eigenvalues because they kind of dictate like everything else. Not kind of. They dictate everything else. If I write down a capital letter, um, I'm more than likely talking about a matrix, and that's very much so the case right now. When I talk with a lowercase, that's going to have a little arrow on top of it. It's a vector. And we're going to finish this equation. What's the right hand side? Of course, we're talking about eigenvalues. So we're going to have lambda that represents an eigenvalue times x, actually. And so you might look at this typically and know algebra enough to say that, oh, well, we just cross out the x's and say a is equal to lambda, which means that since lambda is a scalar quantity, meaning it's just like a number like 4, let's say, because lambda is a scalar quantity, that means that a matrix is equal to a scalar. You can have scalar matrices, but that's not what that A represents. A is arbitrary. It could be any matrix. So how do we have, say, an n by n matrix, A11 to A1n and AN1 to ANN? How do we have this matrix and it's equal to some number lambda? Say you have like, I don't know, a 2 by 2 matrix here, and it's like A B C D. Gorgeous. This is what this is going to look like explicitly. I think that's like how you might call it. I'm gonna make sure you're recording. You better. Yeah, I'm gonna kick your ass out. I think this is the explicit format. This is some matrix A, and we're gonna multiply it by x1 and x2, let's say. Right? There's a 2 by 2, 2 by 1. Yeah. So that'll result in another 2 by 1. So let's say that this comes out to, this is our A and this is our X. This is a vector. Yeah, that makes sense. A vector is going to be either a line of numbers vertically or a line of numbers or whatever it may be, functions, I guess. I haven't gotten that far yet. Horizontally. In this case, we have them vertically. It is a column vector. If it were otherwise, then we'd have a little multiplication problem here. But that doesn't matter because I already said I don't care about. I care about you. I don't have the time to go over how matrices work. Figure it out. Let's say that this comes out to 10 and 30. I don't know if you heard my stomach coming out of my mouth just now, but Ignore it if you did. Let's say you get 10 and 30, because this is a 2 by 2. This is basic times a 2 by 1. You need these guys to be, I'm already contradicting myself. You need these guys to be the same. They kind of cancel, you forget about them. And these ones here, they come together to make a 2 by 1. This is just a column. It's a column vector. That's what this is right here. It's going to result in a column vector. We get, say, the numbers 10 and 30. This is kind of our left-hand side of the equation, right? We have a and x, so this is our lambda x. Well, where's the lambda? I only see an x, and it's not even the same x, but this is just assuming that we have some arbitrary values. This is the output right here. So whatever input in here gives this output, and this is our vector being multiplied by some number, which means essentially if we took out some number here, that's like the common factor in it. So this is where it kind of works algebraically. You can look at this and say that it is also equal to 10 times a column vector that's 1 and 3. You see that? You multiply in the 10 to every element. There's only 2 of them, not that hard. 10 times 1, 10 times 3. You get 10 and 30. This is lambda in this case. This is the eigenvector. Do I know what it represents actually? I already answered that question. I don't know conceptually. So in this case, we have 1 and 3 for x1 and x2. And this is our eigenvalue here, our proper value. These are important things. Obviously, I'm learning them. Physics major, whoop-de-doo. But that's the beginning. Okay? But how do you get lambda? How do you do it? I mean, like if we have a, how do we get lambda? Well, my friend who knows say shit. My friend who knows about matrices and whatnot, you know what a determinant is, right? Perfect. Awesome. Do I know what it is? Funny you ask. I don't know what they represent. Stop bothering me about it, though. You also know what the identity matrix looks like. N by N identity matrix. Only the diagonals have ones. The rest are zeros. That's represented by I. That sounds random. It's kind of coming out of nowhere, but it matters because it comes up in this equation. D of lambda, which is just how my book writes it. I would just call it determinant here of something. So let's see, starting the same thing about in. It's A, our matrix, I already know. And that equation, I'm double checking this. Good, stay like that. A minus lambda, our scalar quantity, times I, we're going to subtract lambda I, and we're going to set it equal to 0. And funny things will come up. We get to do some factoring, algebra 2 and stuff. You remember them? I certainly do. I have indigestion and I'm trying to get rid of my bloating right now. So we have this little process here. That's so neat. And this is actually really simple. Really super simple. Treat lambda kind of like you would in algebra with x, let's say. This is I. Okay, what happens if you multiply lambda across that? That's what this is doing, right? Oh, and it looks like this. See if you believe it. Lambda, 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 again, what gives? We're going to subtract that from this dude, and we're going to find that it only subtracts from the diagonal. We're going to do matrix stuff to get the determinant. That'll give us a characteristic equation, which means that we are going to have factors of lambda, more than likely. So we might get to do, like I said, some algebra. That's so exciting. A, B, C, this is our A matrix minus, low-key, I might be wasting my time by teaching this part because there's other stuff I need to get into. But we're doing it anyways. Man. This, right, this is what's inside, but we're making it with a determinant. Okay, so forget about this. Look. I said this 2 seconds ago. If you can't figure out what I'm doing, then you're not listening properly, okay? Look, boom, bars. Look at that. Look at that. What does that mean? Do the determinant, man. You know how to do this. It ain't that hard. It's not a 3 by 3 and above. So there's no cofactor expansion. AD minus BC. Look at that. Nice and easy. Multiply this guy out. I want to see it, right? I'm not going to do it. You're going to get a lambda squared in there, right? We have minus a lambda and minus d lambda. Lambda squared is in there. AD, fun stuff. All minus BC. In this case, it's not clear how to factor it, but generally how it'll go is you'll have, you'll figure it out. Some constant will disappear or go into these, right? You factored a quadratic before or a cubic. We have cubics often. They suck. I should practice them. I'm not going to do that. Right? These are roots is equal to A. Gorgeous. Lambda 2. Well, that's just D. That's awesome. We just cleared one of the eigenstuffs. That's amazing. We just got eigenvectors. There can be multiple from one from one. That's pretty cool. Oh man, I'm actually so cooked. I have a presentation to write too. We now know how to get an eigenvalue.